In today's class, we are going to look at buffer solutions. We'll start by looking at what a buffer solution is. A buffer solution is a solution that has the capacity or ability to resist changes in pH when an acid or alkaline is added to it. A buffer solution consists of either a weak acid and its conjugate base or a weak base and its conjugate acid. Example, we can have a buffer solution made up of acetic acid, which is a weak acid, and sodium acetate that happens to be a salt of its conjugate. And example two, we can also have a buffer solution that is made up of ammonium hydroxide, which is a weak base, and sodium chloride, which is a salt of its conjugate base. Types of buffer solutions. Buffers are broadly divided into two types. So we have the acidic buffers and the alkaline or the basic buffers. So let's start by looking at the acidic buffers. Acidic buffers are solutions with pH below 7.0. And these solutions consist of a weak acid and a salt of the weak acid. An example of an acidic buffer solution is a mixture of acetic acid and sodium acetate of pH around 4.75. So as you can see, this is an acetic acid, a mixture of an acetic acid, which is the weak acid, and sodium acetate, which happens to be the salt of the weak acid, acetic acid, and the strong base, sodium hydroxide. Basic or alkaline buffers. Alkaline buffers are solutions with pH above 7.0, and these solutions consist of a weak base and a salt of the weak base. An example of an alkaline buffer solution is a mixture of ammonium hydroxide and ammonium chloride of pH around 9.25. And what you also have to notice is that the ammonium hydroxide is the weak base and the ammonium chloride is the salt of the weak acid, ammonium hydroxide, and strong acid, hydrochloric acid. Standard buffers. A standard buffer is a solution whose pH is accurately known, and they are used for the calibration of pH meters and accurately prepared from pure chemicals. They are normally in liquids or tablet forms and contains accurately measured proportions of substances. When the tablet is dissolved in water, a buffer solution of a known pH is produced. So these are all standard buffers, and this comes in a liquid form and this comes in a tablet form. So example of some standard buffer solutions are 0.1 molar acetic acid and 0.1 molar sodium acetate of pH 6.5 at 25 degrees Celsius, and also a reaction between 0.01 molar potassium dihydrogen phosphate and 0.01 molar disodium hydrogen phosphate of pH 7.0 at 25 degrees Celsius. Composition of buffer. To effectively maintain a pH range, a buffer must consist of a weak conjugate acid base pair, meaning either a weak acid and its conjugate base or a weak base and its conjugate acid. And the use of one or the other will simply depend upon the desired pH when preparing the buffer. For example, the following could function as buffers when together in a solution. So example one, we have acetic acid, which is a weak organic acid, and a salt containing its conjugate base, which is the acetate anion, such as sodium acetate. And two, pyridine, which is a weak base, and a salt containing its conjugate acid, pyridinium cations such as pyridinium chloride. And three, ammonium hydroxide, which is a weak base and a salt containing its conjugate acid, the ammonium cation, such as ammonium chloride. Standard buffer. So let us look at the uses of buffer. Buffer solutions are used in fermentations, in food preservatives, in drug analysis, in electroplating, activity of enzymes, and the blood oxygen carrying capacity in the human body. Characteristics of buffer solutions. 1. The pH of a buffer does not change on dilution. 2. The pH of a buffer does not change after adding small quantity of acids or bases. And 3. The pH of a buffer does not change on keeping for long time. So these are some of the characteristics of buffer solutions. Let's look at some terms in buffer solution. So buffer capacity, buffer action, and buffer range. So we'll start by looking at buffer range. When we talk of buffer range, is the pH range over which a buffer acts effectively. And buffer capacity is the measure of the amount in moles of an acid or a base required to change the pH of a given volume of a buffer by plus or minus 1 pH unit. And what we should also know that the more similar the concentration of the mixtures is in a buffer, the greater the buffer capacity. Example, if we should have a buffer which is made from 0.5 molar acetic acid and 0.5 molar sodium acetate, and also a buffer which is made up of 0.5 molar acetic acid and 0.2 molar sodium acetate, it is expected that the buffer which is made up of 0.5 molar sodium acetic acid and 0.5 molar sodium acetate should have a greater buffer capacity than the buffer prepared from the 0.5 molar acetic acid and 0.2 molar sodium acetate, because the more similar the concentrations of the mixtures is in a buffer, the greater the buffer capacity. Buffer actions. It is the ability of a buffer solution to resist changes in pH value on the addition of small amounts of an acid or a base. Good buffers. A good buffer is one that has the ability to maintain its pH, and most often the components of a buffer are the conjugate acid-base pair of the weak base or weak acid. So for this reason, strong acids and strong bases that dissociate completely in water makes very poor buffers, whilst weak acids and weak bases that partially dissociate in water makes better buffers. And the most effective buffer contains equal concentration of an acid and its conjugate base, or equal concentration of a base and its conjugate acid. And a buffer that contains approximately equal concentrations of a weak acid and its conjugate base in solution is equally effectively at neutralizing either added base or added acid. So let's see how a good buffer works. A good buffer is able to resist pH changes when the two components, and these are the conjugate acid and the conjugate base, are both present in appreciable amounts at equilibrium and are able to neutralize small amounts of other acid and basic in the form of hydroxyl ion and hydroxyl ions when added to the solution. Good buffers. Good buffers have the following characteristics. One, high water solubility. So most biological and chemical reactions occur in aqueous environment. Therefore, a good buffer must have the ability to dissociate well in water. So two is a good buffer must have a low metal chelating capacity. So what you have to note is that the good buffer must have a low metal chelating capability, because if a buffer reacts with cations or any chelating metals in your system, the buffer becomes less effective because it cannot handle additional hydrogen ions. A good buffer must have a high chemical stability. A good buffer is stable and will not break down under working conditions. It is not easily oxidized or affected by the system which is being used in. And for a good buffer, must have a light absorption. So, under the light absorption, what you have to notice is that a good buffer must not absorb UV light at wavelength that may be used for readout in photometric experiment. And finally, a good buffer must have a minimum effect on dissociation from changes in concentration and temperature. Common ion effects of buffer solutions. Common ion effect is the shift in equilibrium that occurs because of the addition of an ion already involved in an equilibrium reaction. The common ion effect as a result causes reduction in solubility and helps buffers to resist changes in pH when either a small amount of acid or base is added to it. Example, in a saturated solution of silver chloride and at equilibrium, we will have the silver chloride dissociating to form silver ion and chlorine ion in the aqueous solution. When a solution like sodium chloride is added to the silver chloride solution, the equilibrium will shift towards the left to form more of the solid silver chloride because of the common ion effect of the chlorine ion from the sodium chloride solution, and these as a result will cause a decrease in the solubility of the silver chloride. And this is an illustration to show how a common ion effect shifts the equilibrium towards the left upon the addition of sodium chloride solution to silver chloride solution. Buffer action mechanisms. So we are going to look at the buffer action mechanisms on acidic buffer and basic or alkaline buffer. So we'll start by looking at the buffer action mechanisms on acidic buffer. Taking the acidic buffer containing a mixture of acetic acid and sodium acetate in aqueous solution as an example, at equilibrium, the acetic acid, which is a weak acid, will undergo an incomplete dissociation to form acetate ions and hydrogen ions. Also, the sodium acetate, which is a salt of the weak acid, and the strong base sodium hydroxide will undergo a complete dissociation to form acetate ions and sodium ion. And the water, which is used in the preparation of the buffer, will also undergo an incomplete dissociation to form hydrogen ions and OH ions. So let's see what happens upon the addition of an acid and a base to this acidic buffer. So let's start by looking at the action of acid on this acidic buffer. When a drop of strong acid like HCl is added in the above buffer solution, hydrogen ions from the added acid will react with the acetate ions to form a feebly ionized acetic acid. The ionization of this acetic acid is further suppressed due to common ion effect, so pH of the solution not affected. Action of base on the acidic buffer. When a drop of strong base like sodium hydroxide is added to the above buffer solution, OH ions from the sodium hydroxide will react with the free acid to form undissociated water molecules, and this helps to maintain the pH of the buffer solution. So this is the chemical reaction explaining the action of a base on an acidic buffer. Basic buffer. Taking the basic buffer containing the mixture of ammonium hydroxide and ammonium chloride in aqueous solution. At equilibrium, the ammonium hydroxide, which is a weak base, will undergo an incomplete dissociation to form ammonium ion and OH ions. Also, the ammonium chloride, which is a salt of the weak base and the strong acid HCl, will undergo a complete dissociation to form ammonium ions and chlorine ions. And the water, which is used in the preparation of the buffer, will also undergo an incomplete dissociation to form hydrogen ions and OH ions. So let's see the action of acid on this basic buffer. When a drop of HCl is added, hydrogen ions from the acid will react with the ammonium hydroxide in the buffer to form undissociated water molecules. And these, as a result, will help to maintain the pH of the buffer solution. So this is also the chemical reaction or equation explaining the action of an acid on a basic buffer. Now, let's see the action of a base on the basic buffer. When a drop of sodium hydroxide is added, OH ions from the added base will react with the ammonium ions to form a weakly ionized ammonium hydroxide. This ammonium hydroxide is further suppressed due to common ion effect, so the pH of the buffer not affected. Buffers in living systems. The three primary major buffering systems in the human body or living systems are carbonic acid bicarbonate buffer, phosphate buffer system, and the plasma protein buffer system. So this is a carbonic acid bicarbonate buffer system. This is also the plasma protein buffer system and the phosphate buffer system. So blood contains four main components. We have the plasma, which is the liquid part of the blood, and normally is made up of dilute solution of salts, glucose, amino acid, vitamins, urea, proteins, and fat. And we also have the platelet, which is involved in blood clotting. We also have the white blood cells, which is involved in immune system, and we have the red blood cells involved in carrying oxygen. The human blood mostly contains the carbonic acid bicarbonate buffer and the plasma protein buffer. The normal blood pH is 7.4 and its arterial pH varies between 7.35 and 7.45 without being pathological. There are two organs responsible for regulating carbonic acid and bicarbonate concentration in the body. And these are the lungs, which is through respiratory functions, and the kidney through metabolic function. The carbonic acid bicarbonate buffer system is the most important buffer for maintaining the pH homeostasis of the blood. In the human body system, gaseous metallic waste carbon dioxide reacts with water to form carbonic acid. The carbonic acid then dissociates into hydrogen ions and bicarbonate. The dissociation of the carbonic acid to bicarbonate helps to resist dramatic change in the pH of the blood. The bicarbonate ions serve to neutralize acid, example lactic acid or ketose bodies, introduced to the body through other metabolic processes. Likewise, any bases are neutralized by the carbonic acid. This equation here shows how the bicarbonate ion in the form of potassium bicarbonate neutralizes lactic acid introduced into the body to potassium lactate and carbonic acid. Protein buffer system. Protein molecule in the protein buffer system contains a large number of ionizable groups, of which some takes up hydrogen ions. Example is the free amine group of the lysine, and some releases hydrogen ions to neutralize OH ions. An example is the carboxylic group of glutamic acid. Questions and answers. The first question says, how does the bicarbonate buffer system buffer a strong acid? The buffering capacity of the bicarbonate buffer system lies in its ability to neutralize the excess number of strong acids by converting them to weaker acids and carbon dioxide and water. The next question says, what is the role of bicarbonate in the human body? Bicarbonate helps keep a normal acid base, which is the pH balance in the blood, by neutralizing any acid introduced into the blood. This balance prevents the body from becoming too acidic, which can cause many health problems. And the next question, what is the difference between bicarbonate and carbonic acid in the blood? Whilst in the blood, bicarbonate neutralizes acids in the body, whilst the carbonic acid neutralizes bases. Henderson-Hasselbalch equation. The Henderson-Hasselbalch equation provides a relationship between the pH of acids and their pKa, so which is the acid dissociation constant. The pH of a buffer solution can be estimated with the help of this equation when the concentration of the acid and its conjugate base, or the base of the corresponding conjugate acids, are known. The Henderson-Hasselbalch equation can be written as this. So, where pKa is the acid dissociation constant, and this denotes the molar concentration of the conjugate base, and this also denotes the molar concentration of the weak acid. Therefore, we can say the Henderson-Hasselbalch equation can also be written as this: pH equals pKa plus the log of the concentration of the conjugate base divided by the concentration of the acid. Significance of the Henderson-Hasselbalch equation. Henderson equation can be used to 1. Calculate the pH of the buffer prepared from a mixture of salt and a weak acid or a weak base. It can be used to calculate the pKa value, and it can be used to prepare buffer solutions of needed pH. Limitations of Henderson-Hasselbalch equation. The limitations is that it cannot be used for strong acid and strong bases. Estimating blood pH using the Henderson-Hasselbalch equation. A modified version of the Henderson-Hasselbalch equation can be used to relate the pH of blood to constituents of the bicarbonate buffering system. And this is normally and the equation is normally given as this: pH equals pKa of the acid plus the log of this divided by this. So where the pKa is the acid dissociation constant of carbonic acid and it is equal to 6.1, this is the concentration of the bicarbonate in the blood, and this is the concentration of the carbonic acid in the blood. So this equation can be expressed as a pH given as pK plus log of this as equation 1.8 over there. Now, if you are to substitute the pH and pKa values into the Henderson-Hasselbalch equation, we have 7.4 equals 6.1 plus log of this. And the 7.4 is the pH of the blood, and the 6.1 is the value of the acid dissociation constant of the carbonic acid. So substituting the value, we have 7.4 equals 6.1 plus the log of this as equation 1.9. If you are to rearrange equation 1.9, so we'll get log of the concentration of this divided by the concentration of this to be equal to 1.3, because if this crosses the equal sign, it will become minus. And also changing log term to the other side of the equation, so we will have the concentration of this divided by this will be equal to the antilog of our 1.3 over here as equation 1.110. And rearranging this, we will have the concentration of this divided by this should be equal to 20 as equation 1.12. Let's start by looking at the test protocols. So we'll start by looking at the materials and reagents needed for this test protocol. So we have 0.2 molar sodium acetate, 0.2 molar acetic acid, 0.3 molar hydrochloric acid, and pH meter. Standard solutions to be given. A standard solution of 0.2 molar sodium acetate, 0.2 molar acetic acid, and 0.2 molar HCl will be given to students, and working solutions to be prepared in 40 ml. Dilute each standard solution given to 0.1 molar concentration in 40 ml using the equation C1V1 equals C2V2. So let's just look at an example. To prepare 0.1 molar sodium acetate in 40 ml from 0.2 molar standard solution. So using the equation C1V1 equals C2V2. So where our C2 is given at the 0.1 molar, V2 is the final one, which is 40 ml. C1 is the initial concentration, which is 0.2 molar, and V1 is the volume of the stock solution needed to prepare the final concentration 0.1 molar in 40 ml. So making V1 the subject, we have V1 equals C2V2 divided by C1. And if you are to substitute the values into this equation, you get V1 equals this times this divided by this. So V1 will give us 20 ml. So what it means is that to prepare 0.1 molar in 40 ml from our stock solution or standard solution, we measure 20 ml of the standard solution. So that is 0.2 molar sodium acetate and top up to the 40 mils mark with distilled water. Now, using the table here to prepare our test solutions. So what you have to do that the first thing to do is that we mix the contents of each test tubes in the table above thoroughly and measure the pH with the pH meter. So we can see that for the test tube 1, we have 1 ml of the 0.1 molar sodium acetate and 8 ml of our 0.1 molar acetic acid. For test tube 2, we have 2 ml of 0.1 molar sodium acetate and 6 ml of our 0.1 molar acetic acid. For test tube 3, we have 5 ml of our 0.1 molar sodium acetate and 4 ml of our 0.1 molar acetic acid. For test tube 4, we have 7 ml of our 0.1 molar sodium acetate and 2 ml of our 0.1 molar acetic acid. For test tube 5, we have just 9 ml of the 0.1 molar sodium acetate and 0 ml of the 0.1 molar acetic acid. And for test tube 2, we have 9 ml of distilled water. So when we are done mixing this, we calculate the pH for each test tube using the Henderson-Hasselbalch equation. So what you have to note is that from the Henderson-Hasselbalch equation, pH is given as pKa plus log of the concentration of the base divided by the concentration of the acid. Therefore, to determine the pH of the buffer in each test tube, we need to determine the new concentration of the base and the new concentration of the acid in each test tube. So let's just use the test tube 1 as our example. So from the first test tube, for the sodium acetate, we can see that 1 ml of the 0.1 molar sodium acetate was added to 8 ml of 0.1 molar acetic acid from the table to give a final volume of 9 ml. Therefore, we know that our C1 is giving us 0.1 molar, our V1 is giving us 1 ml, and V2 is 9 ml. So we now determine the value for the new concentration as C2 in the test tube. So making C2 the subject, we have C2 equals C1 V1 not divided by V2 from the equation C1 V1 equals C2 V2. So substituting the values into this equation, we have C2 equals 0.1 molar times the 1 ml all divided by 9 ml. So C2 will give us 0.01 molar. Hence, the base concentration or the concentration of the sodium acetate in the first test tube is 0.01 molar. So let's do for the acetic acid in test tube 1. So from the table, we know 8 ml of 0.1 molar acetic acid was added to 1 ml of 0.01 molar sodium acetate from the table to give a final volume of 1. So it implies that our C1 is giving us 0.1 molar, V1 8 ml, and V2 9 ml. So where our C2 is to be determined. So making C2 the subject of the equation, we have C2 equals C1 V1 divided by V2 from the equation C1 V1 equals C2 V2. So substituting the values into this equation, we have C2 equals 0.1 molar times 8 ml all divided by 9. So C2 will give us 0.09 molar. So hence, the acid concentration or the concentration of the acetic acid in test tube 1 is 0.09 molar. So putting these values in the Henderson-Hasselbalch equation, giving us pH equals pKa plus log of the concentration of the base and the acid, where our pKa is given as 4.76 at 25 degrees Celsius. So we will have pH equals 4.76 plus log of 0.01 molar, which happens to be the new concentration of the base in test tube 1, divided by 0.09, which also happens to be the new concentration of the acid in test tube 1. So our pH will give us 4.76 minus 0.95. So the pH will be equal to 3.81. So hence, the calculated pH for test tube 1 is 3.81. So when we are done with this, the third step says add a further 2 mils of 0.1 molar HCl to each buffer and measure the pH with the pH meter and compare these values with that obtained by calculation. And I will also encourage students to meet and discuss the table before practical session, and also take note of test tube 5 and test tube 6. So this is a question for you to just think about. So why is the pH readily measured at 25 degrees Celsius and pH of pure water given at 7? So this is my assumed table of results. So as you can see from the table, we have our test tubes here from test tube 1 to test tube 6, and we have the calculated pH using the Henderson-Hasselbalch equation given over here, and we also have the measured pH without HCl with the pH meter, and we also have the measured pH with HCl with the pH meter. So from the table, we can say that test tube 1, the calculated pH is 3.81, the measured pH using the pH meter without addition of acid is 3.80, and upon the addition of HCl, the measured pH is 2.83. For test tube 2, the calculated pH is 4.39, the measured pH that's without HCl is 4.40, and the measured pH with HCl is 3.89. For test tube 3, the calculated pH is 4.94, the measured pH without HCl is 4.94, and the measured pH with HCl is 4.92. For test tube 4, we have the calculated pH to be 5.36, measured pH without HCl is 5.37, and measured pH with HCl is 4.97. For test tube 5, we have the calculated pH to be 8.87, measured pH without HCl is 8.87, and the measured pH with HCl is 6.41. For test tube 6, we have the calculated pH to be 7.0, the measured pH without HCl is 6.98, and the measured pH with HCl is 2.41. So explanation of the result in the table above. So first of all, what you have to note is that a good buffer is one that has the ability to maintain its pH. And also, buffer action is the ability of a buffer solution to resist changes in pH values on the addition of small amount of an acid or a base. So from the table of results, change in pH upon the addition of HCl to test tube 1 is 0.93. Test tube 2 is 0.51. Test tube 3 is 0.02. Test tube 4 is 4.04. Test tube 5 is 2.46. And test tube 6 is 4.52. And the change in pH value is just the difference between the measured pH without HCl and the measured pH with HCl. So comparing the change in pH values, we can say that buffer in test tube 3 is the best buffer and has the greatest buffer action. So these are some try questions that I would like you to take your time and just go through and solve them. So this is Try questions 1. So this is try question 2. And this is try questions 3. I'll just encourage you just to take your time or meet as a group to discuss the various questions. Thank you.